Hello dear students, myself Dr. Biswambhar Mohanty, HOD Department of Physics, Government Polytechnic Jajpur. Now, today we will discuss the experiment to determine the spring constant or force constant of a spring by using Hooke's law. To determine the spring constant or force constant of a spring by using Hooke's law. So what is Hooke's law? Hooke's law states that according to Hooke's law, within the elastic limits stress is directly proportional to strain. So that limit up to which on removal of the deforming force the body comes back to original position, that is called the elastic limit. So within the elastic limit, the stress is directly proportional to strain. This is the basic concepts. And stress means the restoring force per unit area. This is the stress. And strain means we are dealing with this in this case only discussing the longitudinal strain, that is change in length by original length. This is the strength in longitudinal strain. So this is the stress by strain. Stress is directly proportional to strain within the elastic limit. So this is the force. Force means this is the restoring force or applied force you may take. So this is the restoring force is directly proportional to delta L. Delta, this is the if it is applied force or restoring force, and this is directly proportional to delta L, that is F is restoring force. If it is taken, F is equal to delta L or delta L is equal to K, that is equal to X. So this the restoring force is directly proportional to delta L. Delta means elongation or compression of the spring. A delta L is related as X, that is the elongation or compression of the spring. So F is equal to K into X or minus Kx, or F may be, this is taken as a magnitude, F is equal to Kx, or F taken as minus Kx. That means the restoring force and displacement are in opposite direction. I have taken only the magnitudes. So F is equal to Kx, so this is K is known as the spring constant or force constant, and this is known as the spring constant or force constant. So how to calculate the spring constant or force constant? Only by the method of oscillations we can adopt this method to calculate the spring constant or force constant of the spring. You just see so this is the spring. I am giving the basics concepts of this experiment. Then after we will take the reading calculations parts. And this is the natural length of the spring. NL means natural length of the spring. And if it is a block, is suppose this is the natural length of the spring, it is connected to a load. This is the mass M. Load is connected. If it is just gentle released, what will happen? So in the equilibrium position, this is mg, and this is the restoring force hx, and this is the restoring force is kx. Always restoring force tries to brings back to the natural length. So restoring force, this the restoring force brings back to natural length. So in equilibrium, this is the equilibrium positions. This is a natural in equilibrium position. If it is slightly displaced, it will execute SHM. This is the simple harm. It will be slightly displaced, not the elongation is not large, very small. If it is slightly displaced, then it will execute SHM, and this will execute SHM, and its time periods. You know that I will say in equilibrium position, mg is at in equilibrium. Downward force is balanced by upward force kx. So x by g is equal to m by k. K is the spring constant or force constant. So x is the displacement from the natural length. G is the acceleration. And you know that the time period of SHM, T is equal to time period, every time period of a particle execute SHM, the general formula T is equal to 2 pi into displacement by acceleration. So in this case T is equal to 2 pi. In this case this is the displacement from the natural length, and this is the acceleration, means acceleration due to gravity, x by g. So x by g is equal to m by k, that is equal to 2 pi into m by k. So time period T is equal to 2 pi root over of m by k. So this is the time period of a block. This is the block. So this is the mass of the block attached. K is the spring constant, capital is the time periods. Time period means time taken for one complete oscillation. That means if the oscillation starts from this position, this is goes off, then comes back, then down, then comes to the equilibrium position. This is one oscillation. So starts from this position, down, then equilibrium position, then up, then comes back to original position. That is called one oscillations. This is one oscillation. The time taken for one oscillation, that is called the time periods. And the spring constant can be calculated by the method of time periods. In this experiment, by the spring constant can be calculated by method of time period. So in this case, T square is equal to 4 pi square m by k. So k is equal to 4 pi square divided by m by k, T square. 4 pi square divided by m by 4 pi square m divided by T square. So k is equal to 4 pi square divided by T square by m. So this is the formula. From this is the basic concept. This is the force constant or spring constant can be calculated by this method, by this formula. Okay, this is the basic concepts of this experiment. In next part we will discuss the x readings, how to calculate the time period and how to calculate the force constant. So now in this spring constant, in the spring we will calculate the spring constant or force constant. First we will just put the slotted weight 20 gram or 0.02 kg added to the pan. And actually with the help of time periods, method of time period, we can calculate the spring constant. So this the 0.02 kg is placed on the pan and the time just is slightly displaced, very small displacement. 10 oscillation is taken, has to be taken for 10 oscillations. Time by the using, either you may use the stopwatch or you may use the mobile to calculate the time period. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's by using 0.02 kg mass, first time period is 5.03. Then next another observation has to be taken, so that the mean will be more accurate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So its time period is 5.41 second. And another oscillation has to begin. You just take this another oscillation, very small displacement. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 5.28 seconds. So this mean by using this slotted weight 20 gram or 0.02 kg, it's T1, T2, T3 different time period is taken, and it's mean for 10 oscillations, and its mean has to be taken, that T1 plus T2 plus T3 by 2. So again similarly, you just add the another 20 gram, that is a 0.04 kg. So similarly, you can take the 10 oscillations for different 10 oscillations for 0.04 kg, and by using I am giving just one examples how this what is the time period by using 0.04 kg. Just see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So its time period is 6.40 second. So similarly, by using the three observation has to be taken, and by using another additional mass 20 gram, that is total mass is 0.06 kg or 60 gram, or that is 0.06 kg. So a similar 10 oscillation has to be taken for time period to calculate the time period, 10 oscillations, and 3 observation has to be taken, and we can calculate the mean time period. Okay, and next part we'll discuss the calculation part. In the observation, we have first taken the 0.02 kg mass, and having the 3 observation time period for 10 oscillation we have taken, that is T1, T2, T3, and is found to 5.03, 5.41, 5.28, and its mean time period, that is T0, that is for time taken for 10 oscillation we have taken by using the 0.02 kg in kg, that is 20 gram, and 5.24, and time period 1 oscillation is T is equal to T0 by 10. So it's T0 by is for 0.02 kg, time period T0 is taken, and it's for 10 oscillation the time period is 1 oscillation is time is 0.524. Exactly for 0.04 kg, 3 different observation for 10 oscillation we have taken, and for one its mean time period is taken, is the T1 plus T2 plus T3 by 3, and it's for 1 oscillation is mean, that is 1 oscillation 0.0633, 0.633. Similarly, and 0.06 kg mass, and we have 3 different T1, T2, T3 taken through the stop pass or mobile, and T0 is T1 plus T2 plus T3 by 3 mean time period, and it's 10 or 1 oscillation is taken. So first thing you just see time period for 1 oscillation for using 0.02 kg mass, it's 0.524 second, and the T square is thus just taken the square, and for 0.04 kg mass the time is 0.633, and its square is 0.44, and exactly for 0.06 kg mass, and it's one time period for 1 oscillation is 0.764, and T square is this. Why we have calculated T square? Because you know that K is equal to, we have taken K is equal to, so K is equal to, just see, 4 pi square divided by T square by M. We have already derived. T square by M is nothing but the slope of T square for say M graph. So K is equal to 4 pi square divided by slope of T square for say M graph. The pi square, that is equal to T square for say M graph. You just see, if plotted between the T square is because this is the dependent variable and load is taken as the independent variable. This is the mass load in kg. This is M, different masses M1, M2, M3. These are 3 masses taken, and T square is taken. And just see, this is the 0.02 kg, this is the 0.02 kg, correspondingly time period T square, this is the 0.02 kg, and its time period is T square is equal to 0.274, this is 0.274. And exactly, again, it will take the 0.04 kg mass, correspondingly its T square equal 0.04, 0.04 kg mass. Correspondingly, if load is taken as x-axis, T square is taken as on y-axis. So 0.04 kg mass is time period is T square is 0.04. And exactly for 0.06 kg mass, T square is equal to 0.56556. For 0.06, for 0.06 kg mass, 0.06 kg mass, its a time period is equal to square of the time period T square is equal to 0.555. This is the 0.556. And the 10 division is equal to, in the graph we have taken the x-axis 10 division equal 0.1 kg and y-axis 10 division equal 0.1 second square. So if we plot the graph, T square, you just join these 3 points and it is a straight line. And this is the straight line, and from this slope, this is the tan theta, AB by BC. Tan theta gives the T square by M. That is the tan theta gives the T square by M. That is the T square. This is the change in the T square, the change in the mass. So that is tan theta AB by BC. That is the slope of T square versus this is the slope of T square versus M graph. Tan the slope of T square versus M graph. And that is equal to 0.04 minus 0.02. The AB by BC, that is equal to 0.04 minus 0.01. This is 0.04 minus 0.01 BC, and AB is equal to 0.04 minus 0.02. So its time period is found to be 6.66. Slope is equal to T square versus M graph. Slope is find this. So from the graph, you just take the straight line, and this is not passing to the origin, having the negative intercept m0, negative intercept, that's all. You just see from this slope, tan theta is the slope, that equals 0.06. You put the slope of T square versus n graph 4 pi square, pi into 3.141 square, that is 6.66. From the slope we have calculated the slope of T square versus M graph, that is equal to 6.66. By putting this 6.66, we can calculate the force constant. And K is equal to Newton per meter, because F is equal to Kx. K is equal to force constant is equal to Newton, it's Newton per meter or dyne per centimeter. Since we have taken the SI system, that is why it is Newton per meter. And the spring constant, you just see one additional information that, so initially with this spring is actually connected with the load. Initially there is no load, but this is a pan. It having certain, this spring having the certain mass, and this it connected with this pan and spring. If it is taken, it has to be taken into consideration. This is known as the total mass, is known as effective mass. And this effective mass can be calculated by this intercept, So intercept is m0. Suppose the time period there is no T is equal to, suppose this is the spring having the spring mass m, and this is the load, this is the pan connected to this, this is the pan. Initially there is a pan on which the load are placed, sorted weights are placed. This is the pan, its mass is small m, and capital M is the mass of the spring. This is the capital mass of the spring, and small m is the slotted weight. This is the pan, mass of the pan. So its time period T is equal to 2 pi. Its effective mass is equal to m effective is equal to m small m plus m by 3, and that is m0. That is the effective mass is equal to m0, m plus m by 3. Actually, so this is slope m0, intercept is nothing but the, it's 0.02, it's found to be 0.021 kg. So its effective mass is equal to 0.021, that is the x in negative x intercept. This is the x negative intercept is nothing but the its effective mass, that is another effective mass. So effective mass has to be calculated by, also has to be calculated by from this graph, where effective mass means this mass of the spring plus mass of the pan, where on which the loads are placed. So that the effect is calculated by this negative slope of the along the x-axis. Okay, so this is all about the spring constant, how to calculate the spring constant of the spring by using the Hooke's law. Thank you very much.